Okay, looks like another practice test. Grade 12 fields. This is an actual test from years before, so we'll get through this one. Most of your givens are up at the top. If you forget the mass of an electron, mass of a proton, mass of the planet Earth, radius of the Earth, it's all going to be at the top there. And it says, what's the force of gravity between two large rocks in space? One has a mass of 2,250 kilograms. The other one is 4,500 kilograms. They're 4.5 meters apart. It's a knowledge question. Just your basic formula for gravity, universal gravity. 6.67 times 10 to the minus 11. The mass of one of the rocks, 2,250. 4,500. All over top of the separation, squared. Okay, 6.67, 2,250. And then 4.5 squared by, it's pretty small. Scientific notation, 3.35, so 3.34 minus 5 newtons. Okay, what's the field strength 20 kilometers away from a 20,000 kilogram rock? Field strength says how much would a 1 kilogram object feel? So field strength is just going to be a G. I guess only one M right now because the other M is a 1 kilogram test object. So the mass of the rock, 20,000 kilograms, and the distance is 20 kilometers, which is 20,000 meters, and we have to square that. It's going to be a really small number. 6.67 negative 11 times 20,000. And then we're going to divide by 20,000 squared. I think we could do some canceling there. 3.335 newtons per kilogram. 1 kilogram object would experience that much force. Okay. Two charged spheres are sitting 3.5 meters apart. One has a charge of that much, and the other, whoa, bad font here, man. That's negative. I'd have to watch that if that was a real test. Find the magnitude of the force applied between them, whether it's attraction or repulsion. So if they're opposite charged, and these are going to attract, force equals K, Q1, Q2 over R squared. So we have everything we need to know. 8.99 times 10 to the 9. 9.5 times 10 to the minus 5. 6.7 times 10 to the minus 5. All over top of 3.5 squared. 9.5 exponent 5. 6.7 exponent 5 negative. 3.5 squared, divide. I got 4.67 newtons, and it's attract. And last question on the first page. An electron accelerated from rest through a potential difference of 150 volts. So that means 150 joules for every coulomb of charge. But the charge of an electron is 1.6 times 10 to the minus 19 coulombs. Pretty small. It's not going to get anywhere near close to 150, but let's find its energy. Energy equals QV. And the voltage is 150. Electron's not going to get much. 1.6 exponent 19 times 150. 2.4 times 10 to the minus 17 joules. That's what's given to the electron. Well, they said, what's the final velocity? This will turn into EK. Okay, so we got 2.4 times 10 to the minus 17. Mass of an electron, it's at the top of the page here. 9.11 times 10 to the minus 31. V squared we're looking for, divided by 2. So this number's on my screen, so I multiply by 2, divide by the mass of an electron, and then square root that guy. And we get V equals, what's huge? Let's change scientific notation, 7.3 times 10 to the 6 meters per second. All right. Last knowledge question. A wire is a current. Okay, so we're going to find the force. So there's three factors. There's the current, the length of the wire, the field strength, and the angle it comes in at, which is... Okay, so we just got to fill in all our numbers. Here we go. So the current is 4.6. The length of the wire is 1.2. The field strength is 2. A sine of 80. So 80 sine, put this back in normal mode, times 2 times 1.2 times 4.6. We get 10.87. Okay. Thinking. Two positive charges are placed 1 meter apart. Okay. And they're both the same. Okay. A third positive charge is placed to the right of the one on the right, not between them, so that the net force and the charge, this one now in the center. Okay, so we're going to put one over here somewhere. He's going to sit there, and he has a charge of 3.9 times 10 to the minus 4. So this guy in the middle, he's going to be repelled by that guy in that direction. He's going to be repelled because they're all positive. He's going to be repelled to that one. They want to know the value of R so that these two balance out, and that guy just sits right in the middle. This force we can get, no problem. That one there will be K, Q1, Q2 over R squared. We're just going to get this one here, these two guys pushing against each other. And 5.7 times 10 to the minus 4. Oh, it's the same one, I can square that. Distance is 1. Okay. 8.99 exponent 9. 5.7 exponent negative 4 squared. And then divide by 1. Okay, it's 2,000. That's a huge, well, yeah, I remember we said the charges should be between minus 5, minus 6. This is like 10 times bigger. But now we got to have this guy repelling him with the same force. So it's the same formula again. Okay, but my R is going to be the unknown. This force will be the same because I need to balance this one in opposite directions. The Q's would be different, but we can figure everything out. Let's put the numbers in here. .99 times 10 to the 9 R squared. And I got to get the two Q values. I'm going to run out of room. 5.7 times 10 to the minus 4. And here's where we should have planned ahead. And we're solving for R. Okay, so I got this number on the screen. So you have to put him on the bottom, bring him up to the top. Or divide them all across and then inverse at the end. Well, maybe we'll do that. 8.99 exponent 9, divide. 5.7 exponent 4, change sign, divide. 3.9 exponent 4, change sign, divide. Now I have the inverse. Inverse that, and then square root it. R comes out to be 0.827, so okay, I was doing a bit of algebra. Okay, question 4. Proton is accelerated from the positive plate of parallel plate system, passes through a hole on the other side, find the voltage. Okay, so here we go. Positive, negative, and there's going to be a little hole in here. Positive guy's going to fly out the hole. Okay, pass through the hole. The proton exits at, okay, 6.5 times 10 to the 4. And we get the mass of the proton. We're going to get kinetic energy. Mass for proton 1.67 times 10 to the minus 27. Yep. And the velocity was given to me 6.5 times 10 to the 4 squared all over 2. Let's find how much energy. 1.67 exponent 27, change sign. 6.5 exponent 4 squared times divide by 2. I get 3.52788. Okay, that's how much energy was given to the proton. Because it came flying up with this velocity. And now we just have to figure out what was the voltage. Voltage is how much energy is given to a whole coulomb. But the charge of a proton is only 1.6 times 10 to the minus 19. So energy equals QV. I got the energy. I know the charge. Ooh. So I just got numbers on my screen. So just 1.6 exponent divide V equals 22 volts. Okay. A ball with a mass of 3.5 gram charge is released from a point 4.2 meters from another sphere. Oppositely charged, so they are going to attract. So the ball is going to go flying even closer. Okay, so here's the positive charge. No, it's negative. No, charge sphere is 2.4 times 10 to the minus 4 coulombs. And out here at the 4.2 meter mark, we have a little ball here. It's 3.5 grams. It has a charge of minus 3.4 times 10 to the minus 5 coulombs. Mass 0.0035 kilograms. And they're going to be attracted. So they're going to attract together and they're going to fly to this part here. They said it's only 1.5 meters apart. How fast is it going? Because it's got a whole bunch of potential here, less potential here. The potential turned into kinetic. So we're going to find the difference between the two potential energies. So if we go, energy number 1 would be, we're talking K, Q, Q1, Q2 over R. No squaring bottom time, okay? And we'll get energy in position 2 over R. I'll call that R2 and R1 if you want. So I got to find the potential energy here, potential energy there, subtract those two numbers from each other, and that'll tell me how much energy was shifted into kinetic. So if you do the top part, you might want to save that in the calculator. 3.4 exponent 5. Okay, the top is 73. Let's store that in memory. Divide by 4.2. 17.466 joules. Second position. Go back to the same number on the top, and I divide it by 1.5. It's 48.9 joules. Okay, well, these are negative. Okay, forgot that. Okay, so the potential energy did drop. Where did it go? The delta. How much energy was lost? I got those two numbers here. 31 joules. There's the difference between those two numbers. That energy went into kinetic. So 31.4 will equal mv squared over 2. The mass is 0.35 v squared all over 2. Now I have to solve for v. So times by 2, divide by the mass, and then square root that number. And I get velocity equals 134 meters per second. That's a pretty fast moving ball. You just made yourself an electrostatic gun. Okay, protons traveling at this velocity. It enters a 0.51 Tesla magnetic field at 90 degrees. Okay, good. Find the radius of the path. You could derive the formula, but this was one that we probably just memorized this guy. Okay, so we got all the numbers. It's a proton. The velocity, 6.6 times 10 to the 5. Charge on a proton, 1.6 times 10 to the minus 19. And the field strength, 0.51 Teslas. 1.67 exponent negative 27, 6.6 exponent 5, multiply. Divide by the charge and divide by 0.51. And I get 0.0135 meters. Move it over 2 spots, you could say 1.35 centimeters. So the proton comes in and gets pushed around the side. Okay, we got a Millikan experiment here. We got electric plate here. There's gonna be a little drop of oil in the middle here. It's being just held there. We got 450.9 volts and positively charged plate. The bottom is positive, the top is negative, which means this guy has to be positive so that he's being pushed upward because gravity is going to be pushing him down. So that means he's going to have missing electrons. He's got to be positive. Okay, let's figure out what we got here. So the forces would be balanced. So I got mg in the down direction will equal the force in the up direction, which would be the field strength times the charge of that particular particle. Parallel plate system, field strength equals voltage divided by the distance. So let's see if we get all these numbers here. The mass, 1.043 times 10 to the minus 13. Gravity on Earth is 9.8. Field strength would be the voltage, 450.9 over the distance. And Q. So from all this, I have to solve for Q. So let's see. 1.043 exponent 13 negative times 9.8. Now I got to divide by 450.9. I got to multiply by 0.006. And that'll give me Q, which is 1.36 times 10 to the minus 17 coulombs. Okay, but that's for the whole charge. If I divide that by the charge of one electron, let's see what we get. 1.6. I get 85.00, so it's 85 electrons. And it's a deficit of electrons because it has to be positive. Okay, last question, 6. What altitude above the Earth must a satellite be to complete the orbit every 12 hours? So here's the Earth. They're asking for that number, but my formula is based on this distance. And if we want to find 12 hours, so we derived this formula already. This would be probably one that you might want to memorize. You could derive it on the spot. Okay. We have everything here. 12 hours, we're going to have to change that though. 12 times 3,600 seconds is 43,200 seconds. That's going to go inside there. So G, 6.67 times 10 to the minus 11 time, no, the mass of the planet. Everything's up here if you have to look it up. Mass of the Earth, 5.98 times 10 to the 24. G is right there, 6.67 times 10 to the minus 11. Times squared will be 43,200 squared, all over top of 4 pi squared, and then I have to cube root that thing. So let's start cranking numbers out. 6.67 exponent 11, change sign. 5.98 exponent 24 times 43,200 squared times, divide by 4, get pi, square pi, divide by that, and then I got to do cube root, so I'm just going to put in a third, and that gives me 26,616,130 meters. Let's change that into kilometers. So 26,616 kilometers is the total distance here. I wanted the altitude, so I have to subtract the radius of the Earth, which you can always look it up again. The radius of the Earth is 6,380 kilometers is this distance. Okay, so take my total distance minus the distance of the Earth, and then we're back to, oh, I still had it in meters. 26,616 kilometers minus 6,380 leaves me with altitude of here will be 20,236 kilometers. Okay, that's the end of that one.